Hello, everyone. Welcome to the Algebra. I don't know how to spell algebra. Algebra 2 final review. Okay. This will be a comprehensive review over everything we've talked about this semester. And in doing so, I'm going to be using the review packet that has like 37 questions or something on it. Okay. It's pretty long and it is like a practice test almost in the topics that it covers and sort of the questions that are asked. But I'm just going to be straight off right off the bat that the final that you're going to take on the 31st or the 30th of January, and maybe the 31st if you need to finish, will be a lot shorter. The questions will sort of be nested together. So like you'll go through multiple things to answer one question, but it's not going to be this long. Everybody should be able to finish hopefully within that first 55-minute period that we have on Monday. And then if you need, you can also take that Tuesday to finish as well. But hopefully by the end of Monday, we should just be set for the semester. I'm going to be going through each of these problems. And in doing so too, I'm going to write some notes that might be helpful for you. You may use anything that you had from class as notes from the whole semester. So any worksheets that you kept, your book, any packets that we did, and then this thing finally. So write all over this, make whatever notes you need. I'm going to be using this kind of as a problem set and a note sheet all in one. You don't have to complete all of this. You can do as much as you can. You can just watch the video, try to follow along, maybe take some notes here and there. Don't worry about answering the problems. I'm not going to make this as an assignment. You don't have to have it completed. I just want you guys to have any resource that you need to help you succeed on this test. Okay. It is going to cover everything that we've done. You never know what questions from this are going to be on there. It's going to be a lot shorter than this whole packet once again. But I'm going to give myself a hard time limit of an hour for this whole review. Okay, so I'm going to try and do the whole semester in an hour. I've already used 1 minute or whatever of this right now. So let's just go ahead and get started. Okay. So question number 1 is all about patterns, which if you remember early on into the class, the purpose of this unit was kind of just to get you thinking like a mathematician again after summer. And here's what I'm going to talk about for these these sort of pattern problems. What you need to know is kind of the difference between each of the ones that we saw, okay? And really what I mean by differences is how they change, right? How much are you growing by or shrinking by each time if you add on more tiles or something, okay? So in this case, when I look, I'm just gonna start counting up the tiles. I see this one has 1, 2, 3. This one's got 1, 2, 3, 4, 5, 6. And then this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? I'm building this pyramid up or this staircase up. When I look at the changes between each of the pattern designs, in this one I went up +3, and then I went from this one up to +4. And then I can imagine the fourth pattern. Well, what would change is I'm gonna have this same sort of pyramid structure here. So let's see, I need 4 squares, 1, 2, 3. Oh, that was pretty bad. Hold on, let me reset. Oh, I reset everything. Let me just erase this. I want to do like 1 box, 2 box, 3 box, 4 box, 1, 2, 3, and then 1, 2, 3. That's this pattern 3. All I would do is add another row of 5 underneath it. So it's going to look something like that, which would then be +5. And when I look at my changes, I can see this one went up by 3. This one went up by 4. This one up by 5. And that means my second difference, basically what I'm changing each change by, is just +1. And if that second difference is constant, if that's just the same number you're adding each time, then it's actually a quadratic function of some sort, okay? So that's a big thing about patterns. And really what was important about these patterns is that they related to quadratics, which was then the main focus of, well, the first half of the semester. And really, we haven't really left quadratics. We've just sort of added more degrees, or maybe put quadratics in the denominator of a rational function or something. But quadratics and all the things are really the main focus of Algebra 2 in general. And so this answers question A. To figure out how many would appear in design 6, well, if this is the fourth one, then I know in the fifth one, I'm going to be adding plus 6. And in the seventh one, I'm going to be adding plus 7 to this, right? So I go 4, 5. Oh, wait, why did I write 7? I meant 6. The sixth pattern, I add 7. And so in this one, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2, I guess 11, 12, 13, 14, 15 tiles. So it'd be 15 for the fourth design, plus 6 for the fifth design, plus 7 for the sixth design, which is in total 28. So that answers this question. And I'm just using the second differences to do so. You could make a little table, you could write a function if you want, but really just counting them up for the patterns is what you need to know. Okay, and really the second difference being quadratic, that's just kind of a cool fact. Okay, so here we go, we're on question 2. And in this case, this is actually kind of like an Algebra 1 question, thinking about how these patterns change, just number-wise. You can see that each time I'm sort of decreasing, but the amount I decrease by changes, right? And if you notice that each one of these decreases by times 1/2, right? So each of these changes, I'm just taking the previous number, multiplying it by half, or dividing by 2 to find the next, which would mean that the next number, if this one was 8, the next one would be half of 8, which is 4, and then half of 4, which is 2, and then half of 2, which is 1. And then if we kept going, we get into the 1/2s, and then 1/4, 1/8, so on and so forth. But we are asked to just stop here. And really what we want to think about to answer this, linear, quadratic, or exponential. If you know two of them, if you know how two of them change, you kind of know the other. I can tell you right off the bat, it's not going to be linear. It's not linear because we're not changing by the same amount, right? I'm going down by half, which like in this case is minus 64, but in this case is minus 32, right? So it's not linear because it's not the same change. It's also not quadratic because if I keep going and I look at the second differences, like 64 to 32 is minus 32, 32 to 16 is minus 16, minus 8. I'm changing by a different amount each time, right? My second differences are not constant, so it's not quadratic, right? And really, that means it only has to be exponential, which it is. You also know this because it's a geometric sequence, right? You are finding each consecutive term by multiplying by something, which means it's geometric. If you remember from Algebra 1, a geometric sequence directly relates to an exponential function because you grow by multiplying each time, right? Your previous value multiplies onto something, which makes it bigger, and you grow really rapidly, or in this case, decay really rapidly. Okay, so it is exponential. All right, I think that's it for patterns. And then the next thing that we sort of talked about was all quadratics, and we started with the transformations in different forms of quadratics. Okay, so on the next question 5 is going to be really helpful just for notes to write each of the 3 quadratic function forms. But in this case, we see a couple of them here. This one's technically in standard form, but we don't really need to know that to describe the transformations. Okay, so if we're asked a question like this, we always start with this basic parent function, right? We call this the parent function because it is the genesis. It's what everything comes from, and this is just the standard parabola, right? It's a parabola that faces up like a cup, and it meets at the origin. The lowest point is at 0, 0. Okay. Well, what we've changed from this equation to g of x, what we're analyzing, is now there's a minus sign in front, which certainly does something, and there is a plus 11 at the back, which does something as well. Okay. If you want to think about these kind of like linear functions, I mean, that's okay. If you can just memorize the transformations to any function, then whether or not it's a quadratic doesn't really matter. What's important to know is what each thing does. Okay. So this minus sign in front, basically what it's doing is it's taking all of our input values, all of our x things, and making them negative, right? Or actually, it's taking our outputs and making whatever they were before we added 11 negative, because the square is going to keep it positive. But anyway, basically what that's going to do is everything that was positive before will now be negative. So this thing reflects, right? It flips it upside down. This makes it so that the concavity is negative or down, like a frown, okay? And then what this plus 11 does is that it takes every output, right? It's not affecting x at all. So it's really just taking every output and adding 11 to it. Remember, our outputs are y, that's up and down. So if we just add 11, that means we're going to shift up 11. So I'd call this a vertical translation. Vertical translation. I'm running out of room. Let me do it over here. I'll just rewrite the function over here to the left and then describe it. So our g of x is negative x squared plus 11. This minus sign reflects. And it ends up reflecting vertically because everything that was positive before becomes negative. So all the points go up and down there. They reflect vertically. And then this plus 11 is a vertical translation. And this one just follows what it says. Since it's plus 11, we just go up 11. Okay, and that's it. Right, we got our translations, reflections. I don't think we're moving left and right at all because we didn't affect our input x. However, in question number 4, we do. We do actually affect our input because our function is now this. Our original one was x squared, same parabola, but now we have x minus 2 quantity squared plus 5. X minus 2 quantity squared. This is a new thing we haven't seen. We didn't see it in this one. Although this plus 5 does the same thing, right? This plus 5 is just tacked on to the end, which means it's going to be another vertical translation. And it's going to just be up 5. Okay. However, the minus 2 inside the parentheses, this is changing our x values, right? This is taking away from our input. Anytime our x values are changed, we're going to be moving left or right. And so this is a horizontal translation. We just have to know which direction, okay? Now, one way that will work if you just memorize that whenever I add, if I add inside the parentheses, it's actually to the left, but if I subtract, it's to the right, okay? The reason for that is if I'm taking away 2 from my input, that means that all my x values had to be 2 bigger to make up for that, right? Another way to think about it too is like if I input the value of 2 for x, the output of this will be 0, meaning that my new lowest point or my new minimum is now shifted right 2. Okay, so you can think about it 2 ways. If you just memorize, do the opposite inside the parentheses, then you're good. Or you can sort of think about it graphically. You will have access to a calculator, so if you can graph both of these and just tell me the transformations, that's good enough. You're just going to have to do it in the TI-84, which I guess I could show if I pull out this calculator, right? What you would do is you just go on y equals, and then you'd enter any sort of function that you want to do. If you want to put x squared in first to see the transformations, then we could go x minus 2 quantity squared minus 5, or sorry, plus 5, and then graph both of those, and we can see the blue one's going to be our original function, that's just the normal parabola, and the other one's going to be shifted to the right 5 and up, or sorry, to the right 2 and up 5. So this is our red line, our shifted one. It's right 2, up 5. Let me drag that in right here so you can see it better. The red one has been shifted. So those are the 2 transformations. Everything else is the same. The curve's the same. So what I would say for my final answer is horizontal translation right 2. Okay. Another way to memorize these is to just memorize the 3 forms of quadratics, because one of the forms is called vertex form. And as you notice, once again, with this example, oops, I pulled away my calculator. With this example, our original vertex was at 0, 0, but our new vertex was at 2, 5, okay, for our red function. And so I'm going to do vertex form because we just had that one. It looks like this, okay. Oops. Let me get rid of all the ink. Let me get rid of this. We'll just call it some function f of x, doesn't matter, equals, we have this value a in front of all of our three forms. It's going to determine the concavity, okay? But really what's going to be x minus h quantity squared plus k, right? And the things that this does, the h value is your horizontal translation. Oops, let me go purple. It's my horizontal translation. And this is the same thing where if I shift, or if I subtract, I'm actually shifting right. If I add, I'm shifting left. So plus is left, minus is right. And then this one, the plus k, the thing at the end, just is your vertical translation, that's up and down. And if you add with this one, you actually go up. And if you subtract, you go down. So this one follows the rules. And then the a value that's in front is just concavity, right? Meaning it's determining how wide or how narrow your parabola is, right? Depending on the value of it. And then it also depends, if it's negative, then your parabola is going to be facing down like a frown. So if a is positive, then it faces up like a cup. If it's negative, it faces down like a frown. Okay. So vertex form is pretty useful because it tells you all the transformations for it, and that's also just where the vertex is. Okay. The standard form is probably the least useful just by looking at it, but we've also seen it the most now because of factoring. It goes like this: ax squared plus bx plus c, and the c value is your y-intercept. Wherever that c value is always where your y-intercept is going to be. And then your a value, once again, is concavity. It plays by the same rules. And the b value is kind of hard to define. It ends up shifting left and right sometimes. It ends up making it wider and less wide sometimes. So really all you have to think about is that c is the y-intercept, and the value of a determines how wide or how narrow, or whether it faces up or down. Okay, you don't really need to know what b does because it's complicated. And then the intercept or factored form looks like this. It's kind of different, but we oftentimes go from standard to intercept factored form because what we can figure out is it goes like this: a, once again, times x, and then this time minus r1 parentheses x minus r2, okay, where r1 and r2 are roots of the function. Or in other words, zeros, right? They are the places where the parabola crosses the x-axis. So it's the x value of the x-intercepts, okay? And then the a does the same exact thing. So this one's really useful because it tells you where the parabola is. Oh, I forgot my calculator's still up, sorry. It tells you where the parabola is in respect to its x-intercepts. So for instance, like if I was here and here, this value would be r1, this value would be r2. And note that I'm subtracting them. And so once again, it's kind of that opposite thing where whatever the value of r1 is, the actual x-intercept is the opposite of it. Because, well, I guess whatever you're doing, if you're adding, then it's on the left side. It's actually a negative number. If you're subtracting, it's actually a positive number. That's why we write the minus signs here. Okay, so don't forget that. But those are the three forms, and those are useful because they help you graph functions if you need to. But sometimes, though, you might have to solve some functions in a specific form. And so this one kind of is a bit of a tangent. And this one, I know I've done in Algebra 1. We didn't do too many of these. But the big idea with these is to get this thing by itself first. So really, we're going to just solve this algebraically. If you see a function that you need to solve, or a quadratic you have to solve, but it's in vertex form like this, then it's actually easier than factoring, in my opinion. Because what I'm going to do is try and just get x by itself, And to start by doing that, I'm going to subtract this 13 from both sides, okay? And then I end up just getting x minus 2 quantity squared equals 29 minus 13 is 16, right? And then to get x by itself, well, I need to get rid of these parentheses and mainly this square first. So I'm going to square root both sides, okay? Well, if I have anything that's squared inside of a square root, they're going to cancel because this is like the 1/2 power. Square root is to the 1/2 power. This is to the second power. 1/2 times 2 is 1. And so really all I get is x minus 2 on the left. You don't have to write the parentheses too because we really just only have one term now. And then on the left-hand side, or the right-hand side, you have to remember this, okay? Anytime you take the square root of something, there are two possible ways to achieve that number, right? You could multiply. In this case, I know the square root of 16 is 4 equals 4, but I know that negative 4 times negative 4 equals 16, and positive 4 times positive 4 equals 16. And so really what you have to say is, even though that the square root of 16 is 4, the two possible solutions I could have are, not even the square root, plus or minus 4, because they both work, right? They both multiply together to get 16. It's really what the square root is trying to find, okay? And then from here, what I do is get x totally by itself, which I can do by adding 2. You got to be careful. You don't want to just change this to a 6, because really what's happening is now I have this 2 plus or minus 4, right? Which is two numbers, which makes sense because our parabola should have two solutions. And so what I like to do here is think about our two cases. The one case where I'm adding the 4 and the one case where I'm subtracting the 4. And so what I end up with is x equals 2 plus 4 and x equals 2 minus 4. That means that my two answers are x equals 6 and x equals negative 2. And those are my two solutions, right? Two answers for x. Those are 2 points where it crosses the x-axis, as it turns out. Actually, that's not true. It's just the solution to this problem. It doesn't have to equal 0. So yeah, there you go. So don't forget to split up your plus and minus. Don't just combine. That's another thing you have to worry about when you do the quadratic formula as well. Okay, so moving on to 7 and 8, we're going to factor, okay? And then after we factor, we're going to solve. So it's not too bad. Okay, so here's just another recap of factoring. And really, this is what I would call like a level 1 factoring problem, because if I look at the x squared in front, the leading coefficient, or the number that's attached to the x squared, is just a 1, right? Meaning if it's just a single x squared, our lives become a lot easier with factoring. We'll see, I think at the almost very end, a more tricky factoring problem. But for this one, we're really trying to solve this puzzle, okay? We're trying to figure out what two numbers multiply to what's going to be a times c, multiply to a times c, and at the same time add to b, where a and c and b are all just these values. This is a, let me rewrite this better. This one's a, this one's b, and this one's c, right? Just like the standard form of the polynomial, okay? And so I like to set up this little x to be like, I'm trying to figure out these two sides, okay? And really I'm going to put at the top a times c, and at the bottom I'll put b. Well, in this case, a times c is just x squared times negative 8. So I get negative 8x squared. And then b is just the middle term, 7x, okay? So I'm just trying to figure out what two numbers multiply to negative 8 and add to 7, all right? Now, anytime that you have a negative thing that you're trying to multiply to, that means that one of your answers will be negative and one will be positive. And I think in this case, we can see that if I multiply positive 8x and negative 1x, or just negative x, when I multiply them together, I get this. When I add them together, I get this, okay? So these are my two sort of answers to this question. Now, when I draw this, I'm going to draw the area model, okay? But just note, for this type of problem where a is 1, right, where you just have x squared, you actually don't have to use the area model because you've already found your answers. I'll show you in a second. But just a recap of the area model. In the top left box, you always put your first term, the a term. In the bottom right box, you put your C term, the last thing, just the number. And then your B is really the split of these two. It's the negative 1x and the 8x. So I'm just going to put negative 1x there and 8x here. Okay. And then what you're doing is you're basically filling out this Punnett square. You're figuring out what has to go on the edges so that when I multiply them together, it gives me the thing on the inside. All right. So there's only one way to multiply to x squared, and that's just x times x. And so our outsides are just going to be x and x right here. And then what I'm thinking about is x times what is negative 1x? Well, x times negative 1 is negative 1x. And x times what is 8x? Well, x times 8 is 8x. And then just double check, 8 times negative 1 does in fact give me negative 8, which means that these two in parentheses are my factors, x minus 1 and x plus 8. Hey, but guess what? Those were the two numbers we already found just by solving the puzzle. Okay, so the area model is not necessary for these ones, or the box method. But if you're the type of person that just likes to do the same thing every time, you just like the process to not change, then feel free to use it. It also makes you double check your answer so that you don't mess something up. But really, once you find these two numbers, you already have your answer in these forms. Okay. But then if you're asked to solve it, here's what you do. If I'm trying to solve this parabola or this equation for 0, that means that this thing, the thing I just factored, is equal to 0, right? This is what I'm trying to solve. And if you've done the Mathia workspace, this is called the zero product property, what I'm about to do. Meaning, if I want to have this whole thing be equal to 0, the two ways I can do that, because these two factors, these two sort of sets of parentheses are multiplying to each other, if either one of them is equal to 0, then the other one will just get canceled out and be multiplied by 0, right? So it'll become 0. And so what you have to solve are these two equations, okay? If you ever need to solve the quadratic, you just take each thing. So you take x minus 1, and you set it equal to 0, and you take x plus 8, and you set it equal to 0, and your two solutions are just like a one-step algebra problem. You add 1 to both sides, you get x equals 1, and in this case, you subtract 8 from both sides, and so you get x equals negative 8. And really, those are the values of x that make the zeros occur, right? They make the function turn into 0, which means that these are the two values that are the solutions to this equation. The other way to do that is the quadratic formula. It's harder than factoring in some cases, although it might be easier if the factors aren't nice and whole numbers. Okay, so let's move on. When we get this one is a factored form problem. I know that because going back a few slides, it looks like this bottom one with the R1 and R2. And so this one is a factored form. That's the form of the function. And it also looks like our answer from the previous problem, which we factored, right? And then is the graph concave up or concave down? Well, I know concave up is like a cup. Concave down is like a frown. And it depends on this value in front, which in this case is a positive 2. So since this value is positive, since A is positive 2, I am concave up, like a cup. Okay. And then to find the x-intercepts of the function, it's actually not too bad, because that's the whole point of factored form, is to tell you the x-intercepts. But be careful, okay? You don't want to just say, oh, it's our negative 4 and 1, because those are the two numbers. Nah, remember that kind of like, well, in the factored form problem, they're the roots of the function, but we're subtracting in the normal base function, right? And then like in this one, the one we just did, to find the zeros, right, when it's equal to 0, I had to figure out what value of x makes the parentheses 0. So using that same logic, since our function is x minus 4, or 2 times x minus 4 times x plus 1, if I want the x-intercepts, I just want where the output is 0, right? That's where the x-axis is. And so once again, I just sort of apply the zero product property, and I'm answering x minus 4 equals 0, x plus 1 equals 0, not 11, 1. And I don't have to worry about the 2 because if either of these sets of parentheses are 0, it's also being multiplied, so it's just going to cancel out to 0 anyway, which means my two answers will just become x equals 4 and x equals negative 1. And those are where the two x-intercepts are. All right, here we go. We have a graphing one. Luckily, though, they gave it to us in vertex form, which means I can actually place a really important point on the graph. And then from there, I can kind of just sketch it, okay? So this function is in vertex form. And it looks like this, okay? So I have this minus 3 squared minus 4. So minus 3 on the inside, minus 4 on the outside. I can see that when I'm subtracting on the inside of the function, that means I'm going to go right 3. And then on the tail end, when I'm subtracting, this means down 4. And so really all I have to do is I know that my original graph, like this parabola, the one that just basic x squared, I know that that's always at 0, 0. But in this case, I'm going to be down 4, 1, 2, 3, 4, right 3, which means my new vertex will be there. Okay. And then, for this, I could just sketch it. I do actually know what it's going to grow by because of my a value. It's just 1. And so anything I input is just going to have the same sort of shape as a normal parabola, which means as I go over 1 in the x, I just square it, and that's how far I go up. So I know it's going to be like over 1, up 1, over 2, up 4, because 2 squared is 4, over 3, up 9, 2, 3, 4, 5, and then same thing on the other side. And so I know that my graph looks like this to the best of my ability. And that's good enough. Okay, done. Using the vertex. All right, cool. In this case, we're just trying to multiply these together. This is number 11, and it says using FOIL. I didn't really talk to you guys about FOIL. By the way, Mr. Jacobs made this last year, so big shout out to Mr. Jacobs. If you see him, can you say thank you for making the algebra review? And then also thank you to Mr. McGuire for sending it to me because he had access to it. So if you see either of those two teachers, say thank you because I can make this video because of it. FOIL just stands for, it's an acronym. It stands for first, outer, inner, last. So it's first, outer, or I guess firsts, outers, inners, lasts. And that's just the place of the function. It's a way to remember how to distribute. How to distribute. I feel like it would also be a good crossword clue. It has like the good vowels, although F and L aren't F isn't as popular as L is. So really what that means is my function, or if my two things I'm multiplying is this, 3x plus 1 times x minus 3. I first multiply the firsts. So I multiply this to this. And then I multiply the outers. So I multiply this to this. And then I multiply the inners. So I multiply the two things that are inside, or like close to the parentheses. And then finally, I multiply the lasts. So, give me like purple, the lasts. So I multiply the last term to the last term. And so really what that becomes is 3x times x is 3x squared. When I do my outers, that's 3x times negative 3, that's minus 9x. 1 times x is plus x. And then 1 times negative 3 is minus 3. And when you do it this way, you'll always end up with the two terms you want to collect or just combine together in the middle. And this becomes 3x squared minus 8x minus 3. And that's your final answer. You could also feel free to use like an area model, a 2x2 square, put 3x and 1, x and 3, or negative 3, and then multiply them together here. I think we're going to see a problem in a bit that does that for a longer polynomial. But that's basically all you have to remember. Really just keeping your things straight on these problems. Okay, I'm pretty sure this one is a typo, but I'm not sure. I'm just going to leave it up. I think we can solve this equation for x not too difficultly. I think this is supposed to be 15x if I had to guess though. And we would probably use the quadratic formula. But in this case, if we just want to write it as it says, we can just go with this. I'm going to add 15 to both sides. So I get 2x squared equals 32. And then I divide both sides by 2. And I get x squared equals 16. And then when I, oh, whoa, what the? It did it for me. It wrote stuff. Hello? Strange. Oh, I think I was on the magic pen setting. 32. And then I divide both sides by 2. And I get x equals 16. And then x squared equals 16. And then I just square root both sides. And I get x equals same thing as the previous problem. There are two ways to multiply to 16. 4 times 4 positive and negative 4 times negative 4. So x equals plus or minus 4. And that's your final answer. Okay. All right. Next up, I like this one because it tests us on knowledge of our transformations in the 3 different types. Okay. Types of function forms. So we start with this one. Here's what we know about it. We know that our leading coefficient is positive, okay? So this means that we're concave up, like a cup, all right? Which so far is so good. Our graph actually is. And then when I look at this value right here inside of the parentheses, I'm subtracting 8. That means I'm gonna shift 8 to the right. Meaning my vertex initially, like in a basic function, is right there. In this function, it's 8 to the right, but my vertex in the actual picture is to the left. And so I cannot have this thing match this thing for this reason. So it doesn't match. Okay. These proofs and types of things, I mean, really what we are doing is proving something. In order to prove something wrong, you just need to prove one thing about it wrong. In order to prove something right, you have to prove everything about it is right. Okay, so it's easier to prove that it's wrong than it's right. But when we head into this one, right, we know that -3 is the y-intercept. So this is the y-int at -3, which could be the case. I don't have any scale, and that's for a reason. So that could work. But if I started at the beginning, I would see that my a value is negative, which means I'm concave down like a frown. And that means it can't work because my picture is concave up. So it can't work. Can't work because my picture, because my pic is concave up. All right. Last but not least, you have to check if this one will work. I'm just going to go ahead and guess that it can, but we do have to prove each thing. Okay. So just like in the first example, this one's positive, so it's concave up. So that's okay. That's a good thing. So put a check there. And then when I look at my two sort of zeros or my two roots, I have one that's -2. But remember, that means that the actual x-intercept is at +2. And for this one, the +4, that means that the x-intercept is at -4. Which if you look, this one, the negative one is more to the left than this one. Obviously the scale doesn't necessarily matter, but all these things line up. All line up. Everything that I know about this function is true in this picture, so it could work. It's unlikely that this looks exactly like this, but we don't have any scale, so we don't know for sure. All we know is that everything we know about this lines up with this, so it could be the same function, or it could represent the picture. Okay. Next up, we got the quadratic formula. I think we're going to need the calculator for it. And the big thing about the quadratic formula is to just know the actual formula. Okay, so I'm going to write it underneath number 14, and it goes like this. X equals -b. I won't sing the song. Oh, I could sing the song, but we'll just go like this. Okay, so x equals -b. It's always -b plus or minus the square root of b squared minus 4 times a times c, all divided, and the entire right side is divided by 2 times a. Okay? And once again, that happens when a is the leading coefficient, b is the middle term, and c is the constant. Okay? So in this case, in this problem, my a value is 4, my b value is 8, and my c value is -5. And so I'm just going to plug and play. I'm going to write out the whole formula first, and then I might simplify anything I can, but really I'm just going to type it into a calculator to make sure I get the right answer. Okay, so it starts with x equals -8, because b is +8, and I always have a negative b up front, plus or minus the square root of 8 squared minus 4 times 4 times -5. Okay, let me put some parentheses around. That might help me. 4 times 4 times -5, all over 2 times 4. Okay. Well, what that means is this. X equals, I'm going to keep my -8. I'm going to keep my plus or minus, but I do know this now. 8 squared is 64. And then let me bust out my calculator. Let me turn it on the smart. Okay. So then I do 4 times -5. And I'm going to do this. I'm going to leave the minus sign in the middle. So I'm going to say minus -80, right? This whole thing, my 4ac was -80, and I'm subtracting it. So minus -80 all over 8. And what that means is x equals -8 plus or minus 64 plus 80, because it's 64 minus -80. 64 plus 80 is 144. Oh, that's a perfect square. 144 over 8. That means this, x equals -8 plus or minus the square root of 144 is 12. So plus or minus 12 over 8. And then you think about your two cases, the case where I want to add and the case where I want to subtract. I'm going to give myself more room over here, though. In the case where I subtract. And then if you want to just type this all, you could have just typed all of this into a calculator. And then the second time around, I'll do this on the next problem. But the second time around, you just replace the minus sign to a plus sign, or what, vice versa for the plus or minus. But in this case, I can just think about it. I could almost probably do it in my head, because this will be -8 plus 12, which is 4 over 8, which is 1/2. So x equals 1/2. And then -8 minus 12 is -20 over 8. -20 over 8, which is -20 divided by 8 is -2.5. That's -5/2. And those are my answers. X is 1/2, x is -5/2. Okay. So the whole process is really just about plugging it in correctly and then whittling it down. Or you can go kind of crazy mode and just go for doing the whole problem. Whoa. I just want you over here for right now. Okay. Doing the whole problem typed into the calculator all at once. One thing to note about the quadratic formula is that it has to be equal to 0. Your equation has to be equal to 0, because what the quadratic formula does is find roots or zeros. This case is not. So first thing I have to do is make it equal to 0. So I'm going to subtract 9 from each side. Make it equal to 0. Okay. So it goes x squared plus 4x minus 9 equals 0. And now, I'm not going to make this red. A, B, and C are all here. A is just 1 in this case because it's 1x squared. B is 4, and C is 9. It's plus 9. Or sorry, minus 9. It's minus 9. That would have been bad if I plugged this all in. Which means my function will be this. X equals -4 plus or minus the square root of 4 squared minus 4 times 1 times 9, negative 9, all over 2 times 1, okay? And so when I go to the calculator, one thing I can do is just type all of this in at once. I can just go with a new line. I'll just clear everything. I can just type in negative 4 plus, I'll start with the plus, square root of 4 squared minus 4 times 1 times negative 9. And then I'm going to hit enter first. Actually, I should have put parentheses around everything. I should have went and put parentheses around everything first, because this would be negative 4 plus the square root of, oh no, everything's messed up. All right, let me restart. Parentheses first, that way I can divide the whole term in the bottom. So parentheses negative 4 plus square root of 4 squared minus 4 times 1 times negative 9, ending parentheses for the top, ending parentheses for the top, divided by 2 times 1. Hit enter, and I see that that is one of my answers, 1.605. Hopefully I didn't do something wrong. It feels like I'm maybe wrong, but I feel like I'm right there. And so I end up with, what is this? Turns out to be x equals 1.06, or sorry, 1.606, I guess, is enough to round it. And then that's the plus version because I added. So then the minus version, if I go back into my calculator, I'm going to hit double up so I can highlight it again, just hit enter, and it will bring it all back for me. And then I'm going to change my plus sign to a minus sign and hit enter again. And I get 5.605, negative 5.605. So negative 5.606. I said 5, but rounding it makes it 606. Okay, so quadratic formula. If you feel comfortable with it, use it, do the calculator. I really prefer that if you have to do one on the test, write out your whole function, write exactly what you type into the calculator. That way, if you make a mistake, which maybe I did, to be fair, these numbers don't seem exactly right, you know where you went wrong along the way, or I know, so I can give you partial credit. Okay, but if you just write 2 answers and you said, I used the calculator, then I have no idea if you got it right or wrong. Oops. Okay. This is kind of a cool one. We didn't really talk about this, but really completing the square means, if I think about, or we didn't talk about it in this way, if I think about these are the terms that I have, then really what I'm figuring out is what is x plus 4 times x plus 4, right? If x was here, 4 was here, and 4 was here, then the missing box that would be in an area model would be the 4 times 4, which is 16, okay? So this is kind of like a strategy to be able to factor some problems. I'm going to do an example of it in a minute. But if you can realize that you can turn a set of quadratics or a set of factors into a perfect square binomial, meaning you multiply the same thing times itself, x plus 4 times x plus 4, then it might help you factor. So in this case, solving by completing the square, I could do it this way. I can see that in this problem, when I add all these things up, these two combine, like my actual function is this, x squared plus 8x plus 16. That means if I add 16 to both sides, right, then what I get is x squared plus 8x plus 16 equals 1, right? And then you have a couple options. I know that this left-hand side, this whole thing is just this, x plus 4 times x plus 4, because that's what we just did with the area model. And I know that that's equal to 1, which means that x plus 4 quantity squared is equal to 1. I could square root both sides and see that x plus 4 equals plus or minus 1, and then subtract 4 and get this. X equals negative 4 plus or minus 1, and then you have 2 cases, the case where you add the 1 and the case where you subtract the 1. So you get -4 plus 1 and -4 minus 1. That's -3 and -5 are your two values of x. Okay, so -3 and -5. You could solve that using the quadratic formula as well. I think it's just faster to use to complete the square. Okay, so it's like a strategy, you know. If you can do it faster, then do it. Okay, simplifying radicals. The big thing with these is to know your perfect squares. Here's some. And those are just the numbers that when you multiply something together times itself gives you that number. So 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. That's 1 through 10. Okay. If any of these numbers go into these, then you can reduce your radical, because you could rewrite, for example, the square root of 40. I could rewrite this as the square root of 4 times the square root of 10, right? And the square root of 4 I know is just 2, and the square root of 10 is just the square root of 10, right? I could do this maybe a little bit more. I could rewrite this as the square root of 2 times the square root of 5. And so it could be 2 square roots of 2 times square roots of 5, but 2 square roots of 10 is good enough for me. So that's good. And then same thing here. I know that 25 is a perfect square, and so I could rewrite this as the square root of 25 times the square root of -1. Well, I know the square root of 25 is just 5. But the square root of -1 is this letter I, if you remember. And so really this just becomes 5I. All right, square root of -1 is just I. Okay, we're going to talk about this, I believe, in a couple of slides or the next slide, right? So here's what we did with I. We took some what are called complex numbers, things that have reals and imaginaries, I for imaginary numbers, and then we added them up or subtracted them. Okay, and then in the next slide, we're going to do multiply and divide, or just multiply, I think, actually. And in this case, really, you're just combining like terms. So I know I have these parentheses here in the plus, but really this is just 4 plus 2i plus 3 minus I. I have two numbers, so 4 plus 3 is 7, and then I have two I terms. 2i minus I is just I, so it's 7 plus I. That's what happens when you combine all this. For a lot of these, you can think of, like, for all the adding and subtracting, you think of I as just a variable, right? So in this case, 2, I have a positive 2, and then I'm actually going to rewrite this because I'm subtracting a term, like multiple things inside parentheses. I'm going to rewrite it so that I'm going to distribute each of these, so I get -5 plus 4i, right? So distribute. And then I have two numbers. I have 2 minus 5, that's -3. And then I have 6i plus 4i, that's plus 10i. That's your final answer. Okay, so these ones aren't too bad. You can kind of think of I as a variable. However, for these ones, we cannot, because when we multiply i's together, then sometimes the fact that they are the square root of -1 doesn't really matter anymore. Okay, so what that means in this case is, if I distribute this in, I get 2i times 5 plus 2i times I. Well, 2i times 5 is just 10i. I don't know why I'm switching colors so much, right? 2i's 5 times is 10i's. But this time I get 2 times I squared, right? It's I times I is I squared. Well, I squared is the square root of -1 squared. And as we saw earlier, if I have a square root being squared, or I guess we had something squared getting the square root, but either way, these two cancel. And so really, this whole thing, I squared becomes a -1. And so your final answer is 10i plus 2 times -1, which is 10i, sorry, I forgot the I, 10i minus 2. Okay. And if you wanted to write like this, then it would be -2 plus 10i. But these are the same answer. Okay. And then this one too, we just have to FOIL it. If you want to think about it that way, first enters, outers, lasts. So I just want to multiply this to this, firsts multiply by outers. So that's the 5 to the 1i. And then my inners is these two. And then my last is these two, I guess. And so starting out, 5 times 2 is 10. 5 times negative 1i is minus 5i. 2i times 2 is plus 4i. And 2i times negative 1i is negative 2i squared. Okay. Well, I can collect these terms in the middle. They're like, they both have i's. So this really becomes 10 minus I minus 2. And then this time, I squared is still negative 1. So it's minus 2 times negative 1. And so this becomes 10 minus I. Negative 2 times negative 1 is positive 2. So this is 12 minus I. Okay. So most of the time, I is kind of like a variable. You can think about it that way. But when you multiply them, they start canceling out kind of, or the square roots of the nature of them and the square of them cancel out, and you get actual real numbers. All right. So moving on. This time we have sort of jumped a little bit. That was the end of the first test, if you remember. And then this was the start of the second test. So doing all this stuff with polynomials. And it's been about an hour. So my whole plan of doing it in an hour, I don't think is going to work unless I sort of section it off, which maybe I should, because that might be a good break point. Okay. So I think I'm going to call it for right now. I think we're going to leave the first 20 questions to study first. And then maybe later in the week, I'm going to post this second part of the second unit and the last stuff that we do. Okay. So if you're watching this right now in the review week and you're still ready to go, you're ready to keep reviewing, going through this packet, check if I've uploaded the other video. I should hopefully have it up by Tuesday or Wednesday of the review week. And then from that point, you can watch the next 20 questions or so, or 10 questions, 15 questions, and study for the second half. Okay. But thank you for joining me for the first hour, going through all of the first part of the review and the first part of the semester. If you really want to get ahead, I still have those review videos up on my channel from when we actually learned this the first time. And so while those won't match these exact problems, it'll go over some of the techniques if you want to try and just do these problems on your own and see how far you get. Okay. So thank you guys for watching, and catch you guys next time.